think we're ready. Welcome to the last couple of talks, really exciting. What we're going to be doing is starting, I see some people are still coming in, so find a seat, please. We're going to be starting with Darío Pascual at the SDG Group, and the title talk for today is From Prompt to Observability, Machine Learning Ops and Large Language LLM Ops. At the end of the day, I tell you. Degree in Computer Engineering from the University of La Rioja and Master in Data Science at the University of Granada. Machine Learning Architect and AI Engineer Specialist in the Department of Artificial Intelligence, Architecture and Innovation at SDG, specializing in the foundation of data science platforms and a promoter of Data Beers La Rioja. Welcome. Sorry, yes.
Well, hello. Thank you for coming, first of all. I like to introduce my talk, like she said, from prompt to observability, MLOps and LLMOps. And let's start by the index. In this talk, we are going to cover the following points. Why ML platforms are necessary at enterprise level, introducing the well-known MLOps methodology, and our vision of ML platforms, how we can achieve with these kind of platforms full AI observability, introducing the concept of AI stores, how to implement these AI stores in our platforms, and finally, how can we introduce this AI observability concept in our new LLM ops paradigm. So first, before that, let me introduce myself. I'm Darío Pascual Morales, AI engineer and ML architect at SDG Group. And as shown in the map, and for sure every one of you already realized, I'm not from the UK. I'm from a little region in the north of Spain called La Rioja, known by the wines. And I'm not here to talk about me. I'm here to talk about AI platforms and observability. So, first of all, I want to introduce the well-known MLOps methodology. Maybe I can go. Okay, this methodology covers all the ML code lifecycle and treats ML code like traditional code. So we have the first stage, the design stage, where we can take the requirements, the managers can prioritize our use cases. Then we have the model development itself, where we can go with data engineer, model engineer, these kind of tasks. Even the validation of the model once the model is training. And finally, we operate the model, so we can deploy it and use it in production. But with this methodology, our platforms have more requirements that not only complying this methodology force our platform to cover a lot of new necessities, because ML code is only, as you can see in that picture, is only a small part of a full machine learning platform. So if we want to go from the experiment to have a model in production and use it through a lower company, our platform should cover at least these 6 necessities. So starting for the first one, scalability. What we mean with scalability? So the computing power for our ML models is not always the same. As we know, we can have ML models with that requires a small computing power, but we can have hard ML algorithms that requires a lot of computing power. So our platform, even more if we want to optimize our cost, should adapt and grow with our necessities. Okay. The second one is MLOps. As I said, ML code is not the most important thing of our platform, but is still important because we have code and we have to define a life cycle and promote it between the different environments our platform have. The third one, data access. Of course, if we want to create a good ML model, we need to access data in production, but this data is not always accessible by everyone, and it should be like that. Our platform should give us this kind of security features in order to prevent unexpected people to access this productive data. Governance, okay. I think that this is the main topic of this talk. We are going to talk about model governance and AI observability. And why is governance important? In the different industries, we have a lot of regulations, and to comply these regulations, we need to know how our models were built, okay? And this is also important if we want to internal audit our own models, because normally we want to know how many models we have and how these models were built, okay? The next one, development environments. We need to have maybe more powerful development environments in our platforms because we are not doing anymore only experiments, okay? The notebooks, I assume that every one of you know what is a Jupyter notebook, for example, and we are not doing anymore only experiments. We want to create more, I don't like to call it complex code, but different code than only ML experiments. Maybe we can build DAGs, for example, to define our model pipeline, and Jupyter notebooks or notebooks in general are not quite good for other software. And finally, integration. Our models are not isolated in our department. If we build a model, we want to be used through all our company. And for sure, if we have no integration with other departments or even with other services in our company, our models are useless. So putting some order in these necessities, I want to introduce the building blocks of our vision of ML platforms. Okay, so we have two transversal layers that are the infrastructure layer and the operational layer that connect with the other 5 and each other. Okay, so starting from the bottom, we have our data layer where we connect with our data sources, essentially in the machine learning process. The ML system layer itself, where the machine learning takes part, the governance, observability, and explainability layer, that is the central layer of this talk, and I go in more detailed view in the next slides. Application layer that works like a front end of our machine learning platforms. This is where the user can interact with the platform. And finally, this integration layer that, as I said, works as integration with the rest of the company or layer. And the infrastructure and operational are transversal to all of this layer and provide us computing power and operations to our code. For example, that MLOps. Zooming in a little, we have this detailed view of a machine learning platform. I know that could seem complex, but it's quite easy. Starting from the infrastructure layer, we have three components: storage, computing, and event management. By storage, we mean everything that could be storage. For example, code, containers, artifacts, metadata, or secrets. By computing, we mean traditional computing, virtual machines, containers, and every kind of computing. For example, distributed computing like Spark, or accelerated computing with GPUs. And finally, we have that event management layer where we have our event queues that triggers these computing components. Okay. So in the bottom, we have our data layer. As I said, we have here our data origins, our informational origins, but on top of that, we also have data governance and data security, because not every data should be shared with every scientist in the company. And of course, a data access layer that serves as a connector with the ML system layer. The ML system layer takes this data, and we can do here two things: build our own models with our own feature engineering, training process, and validation process, or take this data and pass it to AutoML or managed AI services, and they build the models. Okay. The governance layer, as I said, the main layer of this talk. This layer controls all the machine learning traceability. On top of that, we have our application layer. Here is where the human gets into the platform, and here we have our IDEs, notebooks, data wrangling tools, whatever. If necessary, we have our data labeling tools, data entry tools to create data to introduce it in the data layer, or our service app, for example, dashboard to print how well are working our models. And the integration layer, where we have our API gateways to expose our models, or the same API gateway to read data from other informational external services. Finally, our operational layer. Here is where operations happens. The GitOps, as I said, we treat machine learning code as machine learning as code. So we have to version it in version control systems and promote it between the different environments with GitOps methodology. DevSecOps, when we promote this code to different environments, we should analyze this code, test this code, validate that it's compliant with the security of our company. And finally, the MLOps part, that could be batch or online. And here we define our ML pipeline. We define how our code should take the features, transform the features, create the models, and finally validate it. And if it's an online service, it should be deployed and put in our API gateway. But why observability is important, and why it's necessary to have observability in our platforms? I like to introduce this section reading this quote that said, observability is a measure of how well internal state of a system can be inferred from knowledge of its external outputs. And this is a quote about traditional software lifecycle, okay? But I think that it fits very well with our MLOps approach, because having observability in our ML systems have a lot of benefits. For example, we can be aware of how many models we have as a company. Normally, this is a thing that we want to know. But also, we can know the context in which a machine learning model has been generated. Okay? And if we put together data governance and model governance, we could ensure a full explainability of the behavior of our models in terms of business use. Okay, so I want to introduce for you the concept of the AI stores. I brought forward this concept before, but I want to talk about AI stores, and I will start from the first one, the feature store. that take the data sources and abstract it for the users, creating features, but no matter what they are connecting for. Okay, so we take our data sources and share the features to the users with an abstraction layer. And our models will take these features, and we can create models with our features, and we store and track all the metadata information and hyperparameters or whatever of our models in our model store. Okay, so we covered that 2 stores yet. And finally, in this row, we have our evaluation store. This evaluation store cover and analyze our models once our models are in production. So we can take metrics from our metric store and apply these metrics to our predictions or to our models and have a full picture of how well are working our models in production. And finally, on top of that, we have our explainability store, that when we put it all together, we take information about features, about models, and about the performance of these models in production. We can create a full vision of the explainability of our machine learning models. Okay, I want to go one by one, going through these AI stores, defining the objectives and the benefits of implementing these AI stores in our platforms. So let's start by the feature store. As I said, the feature store is an abstraction layer where we connect with all the company data sources, and we provide the users an interface to consume that features. So the main benefits of implementing these stores are, of course, synergies, because these features will be shared between all the departments in a company, and we don't really recompute the features if we already compute the features, because we can use a feature that other departments create. Then an abstraction. Abstraction is another benefit. As I said, normally create feature is complex, and maybe we have to know to create a Spark code or know everything about the informational data sources. This is hidden for the users. The users only take the feature and use it in the machine learning pipeline. Traceability. Take a note of that benefit, because it will appear in all our AI stores with a different definition, but we also ensure traceability with AI stores. In this case, we ensure data replicability, because if we trace what kind of data and what a snapshot of data used building our models, we can ensure data replicability and create a new machine learning model with data of the past. And notification. This is also important, because an error in data could be an error in our machine learning model. And with this alarm system, we can notify users and they can change the definition of that feature if there is any problem detected. Okay, so the important concepts here are these three. Feature set, that is a logical aggregation of data sources under the same domain. In this feature set, we have features that the features are a definition and the calculation of a specific value that can be processed by ML algorithms, and a data set that is a logical or physical union of M features of N data of M feature set. So if we have 2 feature sets with 5 features each, we can take these 2 feature sets and create a data set with only 6 features, for example. And finally, the life cycle of features. Okay, we define our data source, we define our feature set, define our features, and define our data set. At this point, we no process anything. We start processing when we want to consume this data set. At this point, we only have definitions. Once we want to consume this data set, we process these features, we create the data set itself, and now we are ready to consume. And we are going to consume our data sets to create machine learning models that should be stored in the next AI store, that is the model store, that aims to serve as a centralized catalog of all the machine learning that happens in our company. It provides the main benefits of this model store are decentralizing, because we are centralizing all the machine learning in the same point. Interface, it works as a common interface, so the users and the services will consume the models in the same way. Again, traceability. Every aspect of our machine learning experimentation will be traced, and it will be traced in a unified view. Meaning with that everything will be stored with the same structure. We have data, hyperparameters, or everything related with machine learning models stored in the same way. So here, the important concepts are model, that is not more than a logical entity for a chosen algorithm, related with a set of hyperparameters that we can change and fit in order to create different model versions that are specific representations of models with a particular set of data. And finally, related with other model versions, we can define metrics and artifacts. Every model version should contain a binary with the model itself, and we should have, with these model versions, a set of performance metrics in order to analyze if our model is good or not, to promote it to production. The life cycle here is, first of all, define our model logic, then train a model following this logic we define, register a model version with the binary of the model and the metrics, validate it. If our metrics are working okay, the model is ready, and register this metric next to our model version. And once our model is ready and correctly validated, we are ready to promote this model, and we will trace the information of the production models in our evaluation store. This evaluation store, again, provides us centralizing, because we are going to store all the inference will be tracked in the same place related with their model versions. We also provide a unified technical definition of metrics. I'm here in the last point. Because we want to define metrics across all the company, because sometimes metrics are quite messy, and not every department defines the metrics in the same way. And we want to unify the metrics here in this metric store that is a part of the evaluation store. Again, traceability, we track all the inference with the model version and the data we use to produce that inferences. And we can detect here in the evaluation store if we have degradation in our models, because we store the metrics, the production metrics, and if we define a threshold, we can know if we are passing or not this threshold and detect and easily detect degradation. So the important things here in a evaluation store are the prediction set that stores all the inference in association with the input data that produce them, the metric definition that, as I said, are formal definition of metric that could be applied for the training data or the predictions, and the evaluation analysis and thresholds that are periodic application of a set of metrics to a data set. So the life cycle of an evaluation store is the metric definition, where we define these metrics. We define a threshold associated with that metrics. We store our predictions. We run our analysis, and then calculate the metric and apply the threshold. And if there is any problem with that metric, we can create an alert and notify that something is not working in production, so we can, for example, change the model we are using. And as I said in the introduction, on top of that, we have our explainability store. The objective of this explainability store is to avoid the black box syndrome of machine learning. So normally, we know that our model is making predictions, but don't know why these predictions are making. So with this evaluation store, we can have both feature analysis and model analysis, and then join it in a report. Okay. The important concepts here are model explanation, that are a direct analysis of the model without the predictions, without the need of the predictions. And the prediction explanations that are row by row descriptions of why our model is predicting the outcomes we have. And finally, we join that both model explanation and prediction explanation and join it in a report that can be automatically distributed to the stakeholder, for example. So the life cycle here have two parts. The model explanation that can be calculate the feature impact and the feature effects of our model. Again, without our prediction data, we only have here the model. And then when we have our predictions, we can, for example, calculate bias analysis, or if our model is fair or unfair, and put it all together in a report that could be a file, a PDF, or a dashboard, for example. Okay, so this is all about AI stores. I think I introduced a entity relationship diagram where we can see how these AI stores are connected. On top, we have our feature store that is connected with the evaluation store and model store through the data sets, and the explainability store is connected with our model store and our evaluation store in order to have prediction explanations and model explanations, and we join it on the report part. Okay. So it's been a while since I start talking about AI stores, and I want to talk about some drawbacks or difficulties more than drawbacks of implementing it in our platforms. And as in ML, we have a problem called course of dimensionality when we have a lot of features and to train our models. Here, when it comes to ML platforms, I like to introduce this course of technology dimensionality, because we have a lot of cloud vendors or a lot of technologies that want to cover every aspect of what we need in the different stores. Here we have a bunch of technologies that cover what is needed in feature stores, in model stores, in evaluation stores, or even in the explainability part. And sometimes it's hard to decide only one. And it could be a problem because there are a lot of competition and may cause that some of that service disappear. And if we use a SaaS service, we have to be careful because it could be a problem if we put all our observability directly in a SaaS service and we don't have this service in our platform. And of course, the communication between these services is hard because we have different APIs in every service, and it's not easy for users to learn how to use the feature store, the model store, the evaluation store. Every service has a different API. And on the other hand, if we, as platform developers, provide a unified access layer to all these services, we have to maintain and have our own library, and this is also hard. But it's not only a problem, the communication between each store. It's also a problem, the communication between the stores and all our platform, because, for example, the data layer should connect with the feature store in order to provide this abstraction layer for users and features. Our machine learning system should communicate with our model store, but also the integration layer should communicate with the model store in order to expose our models. And of course, the model will be connected with our computing layer, and the same with evaluation store, because the evaluation of when we apply some metrics to our predictions, we should compute that metrics with our computing layer, and sometimes it's hard to connect everything together. But unless this is hard, I want to show some examples of how we build ML platforms. This first example is a real-world example of an insurance company. As you can see, this platform relies on AWS. So here we have all our computing services of AWS. The data layer is also on AWS. Machine learning happens in SageMaker, but I want to focus in the governance layer. Here we have our feature store. As I said, the feature store is not a service. It's based on code. So we have some Spark jobs that relies on our computing layer, and we write the result of these features into Dynamo tables in order users can access this feature fastly. Our model store is a SaaS service called Neptune AI, and we integrate it with our model machine learning layer with a custom library. Our evaluation store is a bunch of Spark jobs that write the information of the metrics again in Neptune. And finally, our explainability store is a dashboard in Power BI that takes information from a Dynamo table where we put all the information of the different stores. And this is a real-world example, but as a framework, it could be adaptable. And I think I bring a theoretical implementation of this framework in Azure, for example, in Azure Cloud. Again, every service of computing and storage are Azure services, and data layers, ML layers are on Azure ML. Feature store are, again, a bunch of Spark jobs and a Cosmos DB tables. I want to show that our framework could adapt different different cloud vendors. Okay, and finally, last but not least, I want to show how we address this observability, AI observability in generative AI platforms. Okay, so I create a new draw of how we introduce AI stores in Gen AI processes. We have more data sources because now we have unstructured data and maybe user documentation or company documents, whatever, can be introduced in our Gen AI platforms. We don't really need a feature store because we are not creating Gen AI models. We are using it as a service, so we don't really need feature store. But we need our model store because we need a place to store our fine-tuned models. Again, we need an evaluation store, but with some modifications because we have to retrieve the user feedback and the conversational history from the user interface and define new metrics because the prompt analysis is not evaluated like traditional ML. And we can create reports, again, in the explainability store layer. But I think that the most interesting things of this picture is the bottom side, where we have the user interface, the user type a prompt, but this prompt is not the prompt we share with the Gen AI process. We have a lot of prompt templates, chain of thoughts, different retrieval strategies, and we enhance our prompt before we share the prompt with the Gen AI process. And we call that prompt store, okay? And then when our prompt is already on the Gen AI process, we can retrieve documents or have a conversation that will be stored in the tracked store, where we have the user ID with the conversational history and the documents that the user questions retrieve. And we call that tracker store, and the information of the tracker store will be back to our data sources in order to analyze it as traditional information. So I think that this is all from my side, and I'm glad to answer the question if there is any.
Thank you very much. We do have time for 1-2 questions, maybe.
What?
Hi, thank you for the really good talk. And the concept of LLMOps that you talked about seems like something very interesting. And I just wanted to know your insight on / opinion on where exactly you see it going in the future, including with regards to its impact on MLOps.
Okay. We are introducing this LLM methodology in our full picture of the platform because we want to talk with our platform. What I mean with that, we are introducing these conversational interfaces to our platform in order to talk with the data. For example, I'm a data science manager and I want to know how many projects I have in production. So if we add this LLM layer, we can talk with our application and type how many models I have or how many classification models I have in production. And if we have everything with the correct tags and all the data is okay, the model should answer us and we can see it in plain English, for example.
All right, one more if it's quick one.
Thank you. I loved the diagram that you had. I was curious, in the modern data stack, we frequently refer to the semantic data layer where we can map some business concepts or perhaps alternate definitions or alternate interpretations of the features that we have. But I didn't see in your diagram any kind of business mapping. How would that fit in the diagrams that you had?
The intention of the diagram is to be technical. And we also have another diagram that zoom in a little in the data part because I abstract some concepts of this data part. But the intention of this diagram is to be technical and it's not related directly with the business part. Okay, so we want to link the technology stack of a company to our vision of a platform, but it's not related with the business areas. It's only technical.
Thank you very much, Darío. And for those who are staying for the next talk, feel free to move up. Otherwise, we will be starting in about 5 minutes. Thank you very much.
Thank you.